Good morning. Really happy to see all of you here. And welcome to the session about how to create a new JVM language in under an hour. So, my name is Oleg Šelajev, and I come from Estonia. And I work for ZeroTurnaround. At ZeroTurnaround, I'm a developer advocate, so my main focus of current work is to care about the community, go around cool places, talk to smart people, do some kind of research, maybe publish blog posts on our blog called Rebel Labs. I'm also one of the leaders of the Virtual Jug, which is the online-only Java user group, which you can and should totally join. So twice a month you will get excellent sessions from the comfort of your home. And if you have any questions or if you want to chat to me, the preferred social network of my choice would be Twitter, and you can totally ping me and ask any questions. So before that, before becoming a marketing person, the advocate, I was the proper developer. So I have some experience with Java in different settings. And a word about ZeroTurnaround. It's a company that does produce tools for Java developers. And currently we have two main tools. One is JRebel, which can reload code changes in your running Java process immediately, so it speeds up your development cycle, which is a great thing always. And we have XRebel, which is a performance tool for Java web apps. So if you are into that sort of thing, check it out. My employer would be happy. They will send me to more places to talk to more some people, and hopefully everyone will be happy. So if you are still into that thing, today ZeroTurnaround will launch a public beta of a new product called XRebel Hub, which is a performance tool, kind of like XRebel, but is intended for your continuous integration environments, and you can find regressions in your web applications without any significant investment in performance testing. So check that out, and everyone might benefit from this. So without further ado, with all that corporate stuff out of the way, we can focus on creating new JVM languages, and we can focus on actual what this talk is about. First of all, I would like to survey you a little bit about the programming languages that you use. So who uses Java as their main language of choice for solving problems? Okay, pretty much everyone. Do we have Scala people here? Should I avoid jokes about Scala? We have a couple. So, in a sense, any other languages fans? Clojure? 2 hands. That's a sad situation. Groovy? Kotlin? It's a new language. You will get there. So anyway, there are many languages, and they are all created for different reasons. And despite the catchy title, which obviously worked because you're here, we will not create the language right now on stage, because it's even with all the tooling and with all the preparation, it's kind of not that easy to do in 60 minutes and actually explain what you're doing or comprehend what you're doing. So we will look at the example of a toy language and try to maybe see on the code level how it works. And also I want to have a disclaimer that this talk is not very applicable. So if you imagine that after this you will become a compiler guru, or you will start working on incredibly useful languages all the world will use, and that would be a killer of Java, then sadly that is not the case. So, however, it's a very interesting talk, and I hope everyone will learn 1-2 new things, and we all will be happy. So, why do we as developers strive to create new languages all the time? It's because the state of the union is that everything is broken, right? All languages are kind of subpar, and when you work with something, you find issues that prevent you from doing something that you really want, and you try to mitigate that by creating new tools. Kind of like, which this is the premise that sent JavaScript ecosystem into the state that they currently have. And this is the silver bullet syndrome, as it knows. And Hadi Hariri here on the slide has a session about how we tend to invest and invent new tools, trying to solve all the problems, and then we repeat the cycle because there are no tools that are applicable for all the problems. So the same with programming languages. There are many, they all have their disadvantages, and it's an interesting exercise to create one or to figure out how they're created or what drives them. But maybe it's not, it won't be a solution to all your problems. So do we have people who actually work day to day on creating languages? Like somebody who writes a Scala compiler or who is responsible for some DSL somewhere at work to make life of 2 people. Excellent. You will learn very little from this talk. The rest are safe. So next question that we want to ask after we're asking why there are so many, we would like to know, are there any languages that could be called the best? What's the ultimate programming language? And why do we create new language all the time? The answer to that is very simple. Again, because we work on different domains, we have different problems. And there are languages that are more special purpose than others. So you have general purpose languages like Java, or you can have something, a DSL that simplifies life of certain domain experts in your company, or you can have, I don't know, a PHP, the language created specifically to be hosted as easily as possible, despite all other trade-offs that they do differently. And the language creation is all about solving trade-offs differently. So you can have languages that are suited better for fast execution rather than the fast development time in them, or you can have a very simple language that you can build more complex languages upon, like a Lisp, and you will get the flexibility, but then maybe maintaining this higher level language will be your problem rather than somebody else's problem. So with Java, it's kind of very easy. All hard problems are solved in the JVM or on the language level, and we just get to consume that. If you build something from scratch, well, you take on yourself this responsibility. So it's a hard work, and it's always rewarding and cool, but sometimes it's not as rewarding, especially when people start hating your language and they are not buying it. Still, almost all developers that I know we thrive on creating new things and inventing and making things work. Like remember maybe 5, 10, 15 years ago when you just started programming and you created some component and it worked. Like there is a button on the web page and you start clicking that and it works and it does nothing but shows an alert and you're like, yes, it works. And for 10 minutes you just click that button and you're extremely happy that you build the thing and it works. And this is the feeling that drives a lot of personal research and innovation. Well, obviously corporate world is different. So, and part of that, since programming languages are tools that we use daily, we would like to create a better situation with that. So we create languages all the time. Sometimes they're general purpose, sometimes they're very abstract. And one of my favorite examples of programming languages, and just it shows how many there are, is the Piat programming language, in which the program is actually an abstract painting. And the author of that language wanted to name this after the painter, Mondrian. Surprisingly, that name was already taken. So if you think about that, you pick quite an obscure name for a language, for a very esoteric language, and it's taken, then you know that there are very, very many of those. And, well, sometimes you can contribute to that, and sometimes you cannot. But, well, we cannot do esoteric or programming language work day to day, all of us. Some of us have actually to write, consumer applications or business applications to generate the revenue. But in the free time, we can definitely see how it works. So how do you create a language? There is an excellent series of blog posts about creating a language called Enkel by Jakub. And in 20 short, not very short blog posts, he explained and created a small, still small and toy language, starting from defining the grammar and how the program will look like, to what they mean, and how to implement those details. And this is, well, 20 blog posts is not a small feat. Like, I don't know how many of you write blog posts, but you have to do research. And even reading that, it's kind of size of a short book. So it's a lot of effort, and I would totally recommend you go there and check the code examples and play with it, because it gradually builds the language creation. But in a nutshell, any language creation and any language creates of 3 parts. So the whole idea, the general how the language works, you specify a program, and then at the end, that program creates some side effects when it's executed on an actual hardware. Hopefully those side effects are somehow managed by the semantics and the structure of the program, rather than just generating heat to the universe. But this is the black box view of the language. Inside that language, there are certain parts, components of the language runtime that are universal to all the languages. So you will need to have something that takes the initial program and split that into tokens, and that is called lexer. So this is lexer is a program. All those components are programs that takes programs as an input and produce other programs as an output, or a representation of a program. So first we'll have a lexer that takes the code, as we know. It might be a text file, or it might be a painting, or it might be something else. And it produces tokens of strings, basically the identifiers that are reasonable for the language that you're writing. So it just translates the free form into structured stream of consciousness of a developer. Then we have the parser, which is a program that takes this stream of tokens and produces typically a tree of the execution of the program. So it's called an abstract syntax tree, and it shows in a tree structure what this program is about, what it's supposed to do. And then at the end, you take that abstract syntax tree and you produce a program that is executed on an actual hardware. So it could be a JVM bytecode as a result of that, and then you reuse the existing infrastructure of the JVM to execute that, or you can produce the machine code, or you can have a compiler that takes an abstract syntax tree of your language and produces JavaScript to run in the browser, or whatnot. But in a sense, you go through those 3 phases to create something executable from the initial source. And let's look in a very short things into what those problems are. So the lexer is the part that tokenizes your program. What it does, it builds a finite automata of the tokens, and it's kind of is a solved problem. So what it does, takes a file and creates a stream of tokens. This can be done with regular expressions, if you are really interested, or this can be done with a automaton. And lexing typically is a solved problem, so it's just a string manipulation. You take that and then you create the syntax for a language. The next part is the parser. So what it takes the representation of the programs, maybe mathematical arithmetic operations, and then it produces the tree that is logically represents your program. So on this example slide, you'll see a tree that describes an expression where the operator is at the root node and the children are sub-expressions. So parsing your language is also typically from the stream of tokens is the more or less solved problem. There are tools to do that efficiently. This is not where you would invent that much new. So typically you would work on the AST, and then you would like to make this AST run somewhere. And this is the third part where the compiler comes in. So the compiler is this magical program that takes a representation of the program and produces different one. And typically, if you think about working on the AST level, so you take a tree and then you produce a different tree, and then you produce a different tree again, and then again and again, and you can simplify and convert your textual representation of the program into something hardware acceptable. So, and typically you would run that through a series of steps, and you will have multiple compilers that optimize or transform different bits and pieces of your program. There is a really good resource for compiler writers available on that page, and it has links to tons of other resources, books, and blog posts about how to write a compiler. So it starts with the philosophy and how previously the compilers were created, and list the books on how to design that, and you will learn about optimizations, and you will learn about how the actual hardware works, and how to generate code, and all that. And even from this list, you see that it's not an easy task, because, well, if you need to create a compiler and you need to know all that, obviously you're not for a short journey here. So it's a complex task, and we would like to have it a little bit simpler. So if you would like to create a toy language right now, very rarely you would think that, oh, you know what, I would like to read books for like 2 years and then start actually working on something. This is way complex for the modern times. We would like to hack something together, have it working, and then call it a day and move on a different pet project. So if you start working on your own language, the typical stages that you go through creating language are the following. So you create a prototype, and you implement all those required modules, and you have something running. So you have an AST, and you have a program that interprets that. Just basically traverses the tree and says, oh, this is the plus operation. I know how to add two results of two expressions. And you create a prototype, and it's kind of working. And then you figure out, okay, it's kind of slow and it's boring and it doesn't do anything significant. So I will write a virtual machine for that. And you start writing your virtual machine for that. And then you convince somebody else to use this language. For example, that happened with Python, 20 years ago. And people start using that, and people start complaining. And there are two things to complain about a language. And first is the syntax and verbosity and usability and lack of proper constructs that you would like, that you've seen in other languages. And people complain about that. And the second part people complain about is the performance issues. They start to write a program. As soon as you have the ability to write a program, people will write huge programs that crunch a lot of data, do something kind of time-consuming, and then they will start complaining about how slow it is. And this is a typical... Who has seen a complaint about programming language being slow? I know you code like in Java, and you look like you're more than 10 years old, so you should know the jokes about how slow Java is. Knock, knock, who is there? Long pause, Java. So people complain about that, and then you rewrite parts of your virtual machine, and then you create more optimizations, and then you create more compilers inside that runtime, and then you figure out how to do the garbage collection, and all that takes work, and people still complain about that. And then you say, like, okay, fine, I will create a just-in-time compiler, and I will use the state-of-the-art technology, and I will invest like many years into this project. And people will still complain. So you cannot get rid of complaining, but you might get the performance better. So all those stages, and this is how typically the development of your language goes. So it starts with a grammar, and here's an example of a grammar of the language that we will create. And the grammar is the following. So our program will be an expression. This will be a super simple language. Not even like language, it will be kind of like a lame calculator that will not move you far. So our program will be, and this is where we start implementing language. We talk about the grammar, and we would like to define which strings are valid programs and which strings are not valid programs. So the whole world of strings will be divided into separate parts. So to specify the valid programs, typically you would create a grammar. You would create the rules to what is a valid program. In this example, it will be an expression that can contain mathematical operations, it can contain numbers, and it will contain the parentheses. So this program defines strings as programs. This grammar defines strings that can be represented as a tree that we saw just a couple of slides before. So we have the arithmetic operations that can join a couple of expressions, and we would be working with trees like this. So now on this tree, you can easily figure out how to execute this program. You just point at the root node and you start moving a finger to the left and then to the right, and then you compute those sub-expressions and then come back and figure out what the result is. And when you finish with the whole tree, you have the result. So you know how to interpret this AST. Now the interesting part comes in, because you want to create a proper language and you want people not to complain about lack of features that you want. So you will start worrying about how to interpret this exactly. You would start to maybe define variables, and as soon as you have variables of function or namespaces, you will have lexical scoping rules. This is something that JavaScript did poorly, for example. You would need to define some functions, and you would need to figure out the machinery to have the call invocations, method invocations. You would introduce a type system. You would introduce garbage collection. This is a lot of work that is very aligned with the language creation, but it's also quite orthogonal to actually defining the semantics and the innovation in the language. So if you want to create a new language, for example, you want to create a language that will take a picture, a painting as an input, then the innovation comes from interpreting that, right? This is the new cool bit. And then all those things you still have to do to make it usable, but this is a very different purpose of a different path of the innovation. So, but still, to write a language, you will have to, is this working? Yeah, now it's working. So you will have to create that, and it kind of will always seem so close to you, but you will struggle with implementing those things because it's really, really hard, and it's hard, it's time consuming, and it's expensive. So here is a pro tip about software development in general. Solving hard problems is expensive in terms of time, in terms of knowledge that you have to have, in terms of everything. So we know that many problems currently in the world, in software, are not that expensive. You can create a web app or a cluster of web apps in like 40 minutes and deploy that and show multiple features by slapping annotations together. And but the thing is, it's only cheap. When you have a problem that seems hard, but it's really easy to do, that means that somebody else paid for that. So somebody else created the whole research, and you were just standing on the shoulder of giants and reusing their work. Hopefully this running hamster will remind you of that. So what we would like to have with the language, we would like to concentrate on the interesting parts and have all the rest kind of offered for us for free, because we are cheap like that. So what the stages, out of those stages that we saw before, we would like to prototype the language, preferably using Java, because this is the language that we use and know. And we would like to create the semantics and kind of specify how our input program will correspond to some sort of AST. And then when people start using that, they all have the whole infrastructure for them there. It's fast, it integrates with all the tools, it also runs with the platforms that people like and use, and this is what we would like to have. And luckily we have the tools to do that. So enter the growl and Truffle projects. So growl, who has heard of growl before? Interesting. 4 people. I salute you. So growl is a dynamic compiler and an interpreter for the language runtime. So it still is a research project under the OpenJDK currently. And the goal of that project was to build a Java compiler, a high-level compiler that will integrate with the JVM, and the compiler would be written in Java itself, and it would reuse as many features the JVM offers itself, but it will be suitable for compiling different other random managed languages onto the JVM. So, and they created that. So the Kepler University, I think it was the Kepler, if I'm not mistaken. Yeah, it started there. So, and they created the high-performance optimizing JIT compiler called growl for the Java virtual machine. And they utilized the platform. And a couple of things that growl does really well, and how it's different from the typical like C1, C2 compilers that we have in the hotspot. It has a different approach to the inlining. So it better inlines the code. It simulates some executions and can inline the code smarter. So it can be potentially quite fast. It uses different escape analysis techniques, and it does use speculative optimization on top of that. So the goal of the growl was to create a state-of-the-art compiler written in Java and integrate with the existing JVM ecosystem on top of that. So on top of that, on the growl, so when we have the compiler, we would like to have some tools to leverage that compiler. And there is a Truffle. Truffle is a managed language implementation framework that is extremely cool. It's a reasonable implementation of a framework. It builds on the growl, and it has a tight understanding of the works between how it managed the language and how the growl and the JVM execute things. So they can feed the information back and forth between each other and optimize and compile a program really, really well. So Truffle also does some optimizations on the AST level. So it's a framework that is aware that you would like to run your programs fast, and it can speculate about what execution paths are taken in the tree of your language, and it works really well with growl. So there are multiple implementations of the languages that run on the Truffle with growl, but the thing is, if you look at this spider diagram, mad Photoshop skills by me. The Truffle sits in the middle of this whole ecosystem. So on one part of that, you have the virtual machine, either hotspot or growl. You have the compiler. You have different tools. And on the other part, on top of that, you have the languages. So it separates the language from the underlying architecture. So you can have the same tooling. You can have the same infrastructure. You can have the same benefits that the VM engineers introduced to the underlying virtual machine, and use that in different managed languages that are implemented over the Truffle. So there is a JavaScript runtime that currently works there. JRuby runs with Truffle. I think there is a implementation of R, the statistics language that runs with Truffle. And you can easily create a new language that will sit on top of that existing world that solves a lot of hard problems, and you would just focus on creating interesting bits for yourself. So next obvious question, when you know about this, that this sort of thing exists, you're like, how can I get this? I want my hands on this. So to get the growl, you can download the growl VM. So it's a different VM, it's a different executable, and you download that and you unzip it, and you have different paths, and you just overwrite your Java command, and then you can point to there, and you will have the growl VM running. And this is amazing, but a little bit cumbersome, and not maybe the best thing. So there is a different way to do that. So JDK 9 comes with a bunch of new options, and one of them is the XX plus enabled JVM CI. So JVM CI is a JVM compiler interface, and what it allows you with the JDK 9, it allows you to specify what compiler you would like to use, to run in the JVM, And with a bunch of options, just a couple of options, and just providing a jar file that specifies the compiler, you can plug that into your normal JVM. So this work was done as a part of the JAP 243, and the goals of that were to create the interface that allows the compiler and allows pluggable components to access the internal VM state better. So VM is a complex machine, right? There is a lot of things going on underneath. A lot of time and effort has been spent on making those as bug-free as possible and working. So through the compiler interface, you can get some levers into the internals of that, and the compiler gets the access to the bytecode and to the machine code and to the process of producing the machine code for that. And it's really great that it landed in JDK 9, and you can totally try that without downloading much external programs and utilities. So it's there. You can try that. I recommend you trying that. You can try running your programs with that. It's sufficiently, well, it's not sufficiently stable. I would not put that in production. But it's sufficiently stable to experiment with and to try. So this is exactly what we're going to do now. We're going to see how it works, and we're going to try to look at a small example of a toy language for a tiny calculator. So at this point of time, I will try to go to my IDE, which currently happens to be Eclipse. I love IntelliJ IDEA, I use that daily, but for some reason for this project it was Eclipse. So the program here is our language is very simple. So if you download growl, it comes with the language that showcases the features of the growl, and it's called the simple language. And initially I thought that I would show you the simple language and how it works, but in fact it's not so simple. There are tons of classes, and it's not even possible to just figure out what's going on. It's just like with very many features. They have functions, they have function redefinitions, they have imports, they have the polyglot invocation. So if you have different runtimes, imagine this. This is a very cool bit about the growl and Truffle. On top of that, if you have different languages in the same VM loaded, you can interact between those. Your JavaScript code can call your Ruby code, and your Ruby code can call the JVM back, and everything goes through a single point of entry through the Truffle. And then when you think about how huge the program would be and the tree, and then you think about that this cannot be efficient enough, then the Truffle takes that as a challenge and just optimizes a way through the language barriers, and the life gets amazing pretty fast. And you even forget that everything is broken. So, however, in this project, I would like to show you just the most essential parts of the language, building a language with Truffle and a run on growl. So first of all, we'll have the import, and you can just add that into your Maven project by just throwing in a couple of dependencies. They're available in Maven Central, so you just download that as you would do with any dependency, and you get the classes and the APIs to do that. There is a Truffle runtime that you would use, and you would create an engine on which you would execute programs. So the exact program creation here is not that important, but you follow all the steps that you would follow in any language creation. So you get a string somehow, and then you have to parse this string, and then you would have to execute that. So let's look at the grammar for this toy language. For this, I used the UntLR library for generating grammars and generating parsers and lexers from the grammars. And this is how the syntax looks for that. This is exactly the match, not exactly, but this is the match for the grammar, sample grammars that we saw before. So the program consists of an expression, and an expression is either the arithmetic operation or the number. And you can see that we have like 4 arithmetic operations. and the numbers. The cool bit about the numbers is that we allow the dot in the number representation. So we are dealing with floating point numbers here. So we will have integers and floating point numbers. When we have this grammar, the untler will generate us a couple of classes that look like this. They're not very readable by hand, but the API is super straightforward. What we have to do, we just have to parse that running. It will create a tree for you automatically, and then you will just need to parse the tree by providing a listener to run through the tree. So it's a very default algorithm here that you can you go through the tree, and then you have a stack of nodes that we visited before, and when we exit a certain node, we just specify that the next node is the operation. The cool bit about the Truffle is that you can create the type system for your language very easily. So in this toy language, we will specify the types that are, we will have longs, primitive longs, and we'll have big decimal, which will be our representation of the floating point number. So this would be, it can be quite complicated to figure out how to use a type system in the language, and this example shows how easy you can achieve that with Truffle. So you create just an abstract class, and you say that will be my type system. These are my types that I would like to use. You create the language, and you slap annotations on top of that to say like, oh, Truffle, you know what? This is my definition of a language, and I would like to call it this, and I would like to call it that. You provide a context. This is a cool class. So for toy language, you don't have to specify much anything. It comes with batteries included. So you just use a couple of annotations to say, oh, I want this language. And all you have to do is to specify the type system that you'd like. And you need to specify the AST in terms of the Truffle objects. So you create some sort of AST from the grammar in any way you like. And in this example, we would do that with untler. And then to leverage the whole machinery of Truffle and growl, you have to represent that program using, well, objects that Truffle knows about. And those things are the nodes. The nodes are short classes, or maybe not so short, but they extend some Truffle classes, and you have the information about what it does, this particular class, as an annotation. So it all works on the annotations, which is very familiar to Java developers. So this is the example of the leaf node, which is a number. And it will hold our big decimal value there. And when we execute this node, it will just return this value to us. The same we'll have with the long node, where we have just a primitive long value. And the mathematical operations are the same, very simple. You just specify, oh, when I see a plus, I would like to treat that as an add node in my class. Cool thing about Truffle is that it allows you to specialize the execution of the nodes based on the types of the arguments that you receive. So you remember we had two types. So in our program, we had longs and big decimals. And every node that you would like can come with different implementations of the execution logic based on the operand types. So if we have two longs, and we can say Truffle, oh, please execute my method where I would just call this functionality. So we would use the math class, and we say if the arithmetic exception occurs here, then please use a different implementation. So you just hint Truffle that there might be multiple code pass executions depending on the arguments, and it takes care of picking the right one based on the argument types for you. And then you create all the nodes for your language implementation, and they're super simple. So we have 20 classes here. This language probably cannot be created in 60 minutes, but you can read it in 60 minutes. There are 20 classes. That makes 3 minutes per class. If you read fast, you can totally do this. So the title was not lying that much. And in the end of all that, you use the polyglot engine to evaluate a source that will parse parse this source using the untilar API. Just from string, it will go and create a lexer, and from the lexer you create a parser, and then from the parser you create a program. You walk this AST program, and by supplying listener, you create the truffle nodes. So you follow all the steps that you require to follow to create a language, from the parser to the AST, but then on that, you convert that into the terms Truffle understands, and everything else is not your problem, because Truffle takes care of everything. So let's see if it actually works. It worked this morning, so hopefully it will work today. Right now, let me just run this. We are running on Truffle. So as we are creating a calculator, we would expect it to work, and you can see that it indeed works for small values of longs. And as a result of the program, when we execute, we would take the class of the result of this result value and the result itself. This would show us that our type system actually works. So let me try a more complex example here, just to show that this works. If I evaluate this expression, and if there are no bugs in the mathematical logic of how nodes are evaluated, it shows us 10. And you can see that all the values here are integers, so it parses correctly as primitive longs, and it executes the logic on the primitive longs, and it works. So what will happen if I just now take this different expression where the 4 is 4.0, so it's a floating point, and paste it? Who thinks it will be 10? Who thinks it will not be 10, but it will be something else? Well, in a nutshell, it will be 10 because the numerical value is still 10. But as you would expect, the type of this program is different. So the thing is, nowhere. So if we take this multiplication thing, and we'll look at how this evaluation of the multiplication node is implemented. Nowhere we specify let's check the arguments. If they're primitive longs or if they're of this type, let's execute this code pass. Or if they're not, we'll execute this code pass. We just know how to multiply longs or how to multiply big decimals, and the Truffle will figure out how to pick the correct specialization of the code execution based on that. You can also specify more annotations to hint the compiler that, please, you know what, do not inline this. So there is boundaries of what a compiler can and cannot do. There are more annotations you can specify, guards and conditions in the code, more advanced that just like, have my types. You can check for the identity of the objects that are passed to you. So you can, for example, cache the function execution using annotations. And you can, through the annotations, you can leverage the full power of Truffle. How cool is that? It's extremely cool. So now, look at this. So we have big decimal 10.0. If I take a different expression, so here we don't have the 4.0, but we have 1.0 at the end. Who thinks the result would be big decimal 10.0? Who thinks the result would be something different? One person? You think it's a tricky question, right? Surprisingly, the result is a little bit different. It looks different. It's a scientific notation of how we represent this 10.0 number. And since the result comes from just printing out this big decimal, I'm not really sure why it happens. But it does happen. So somehow the representation of that is different. Probably this is just related to the floating point arithmetics rather than the implementation of our language, but it was a trick question. Another good question, if I take two very long values, right, and this is also pretty cool, so it will showcase the specialization. So this big number is a long max value -1. So if I take two very long values and add them together, what will I get? Do I get a negative number? Who thinks I will get a negative number? Who thinks I will get a positive number? Who thinks it will crash? Skepticism, very important. A software developer is an off topic because I have a couple of minutes left. Software development is largely about being as pessimistic as possible. The happy path in the code and in the business logic is very simple, typically. And you just write that, and it is, if everything works, your code is concise and nice and clean and neat and everything. But then you start putting error checks and catching exceptions in there, and you start thinking about all the things that can go wrong, and before you notice, your code is a mess. So being pessimistic from the start is a virtue. It's a good thing. So back to this long addition. So if I execute that, we will get a big decimal value that is the result of those two numbers added together. Why that happened? It happened exactly because we have the Truffle to execute the specialized code path in our code as we specified. And as we specified that if we get an arithmetic exception here, please just fall back to a different implementation. And that is not cheating, I would suggest. That is careful planning. And we will fall back to a more generic implementation of this code path. So if we fall back from the arithmetic exception here, the most general code path is where we add just two operands, just two objects. And here, in this slow code path, we do do all the type checks, and we do instance offs, and we do create the big decimals out of longs, and we add them as big decimals. So, however, we never will specify that, oh, Truffle, please try to use this fast code path first, and then, if it fails, go to the slow code path. The framework is smart enough, intelligent enough to do that for you and know that, well, first you want a fast execution, and if it fails, go to the slow code path. So in this toy language, even with this very limited type system of two types, it's fairly interesting to play around. So it's a very tiny example of the language, and you can totally play with it. If you are interested, if you have never created a language before in your life, it's way easier to start with something small and working than to work through all your learning curves and all the problems from the start and from scratch. And another cool benefit of a Truffle is that everything is in Java, so you don't have to Google what is a dereferencing operator all the time. Was it ampersand? I think it was ampersand. Maybe not. So this tiny demo worked. I think you can access the code. You can access the code somewhere and try. I will put the code somewhere on GitHub and we'll see. So as a result, we looked at this tiny toy language that takes arithmetic expressions and tokenizes that using until R and creating this stream of tokens, and then parses into an AST. Then we traversed the AST with a very simple algorithm and converted that into the Truffle representation of this tree that we execute. And then the Truffle kicks in and executes this thing as it knows how to do, and then we get the result. In a good case, that is a very readable 10.0 result. In a less interesting case, in more interesting cases, it can be something different. So if you're wondering how useful that is and how excellent the optimizations and how excellent the compiler is, then it is pretty cool to know that for general workflow and general benchmarks, it is quite sophisticated for different languages. So Ruby running on Truffle and growl is quick. R is extremely quick. So if you do statistics, you can try. It's not the full implementation of the R, there might be deficiencies in its very early alpha. You can see that the Java thing, and those results are not by me, but they are by people behind the Truffle and growl. In the Java part, the performance of your program is on par very often with the normal execution of the just normal JVM, the hotspot, right? So for patterns, for the bytecode and program patterns that are less common in the Java world, for example, if you use a different JVM language, you can get the benefit of the speed up from this new infrastructure for the compiler that growl offers. So it takes a different path. So for less common idioms, it might be better than the hotspot. So you can see the Scala, and well, it's a really great effort, and it's a very interesting project. And now it comes to Java 9, and hopefully we'll get more and more eyes and hands on working with that, and it will become better and better. Now, if you want to create a language, and you will need to start with a grammar, there are multiple libraries and frameworks how to transform and how to implement the grammar. In this example, I used Untilar, and it's a very solid library. They went through multiple implementations of parsers and how to create grammars. There was a book about this, and they are excellent about this. And at the end, if you want to create a new language, you have to remember that any language consists of two parts, very loosely defined. It's a runtime system, and it's a library or the ecosystem. So to have a successful language, you have to have both. And if you are interested in one part of that, you would largely want to reuse the whole knowledge and the whole effort that was put into the other one. So if you want to create a new grammar and a fancy esoteric language, you would like to reuse the whole infrastructure. Or if you want to use and work on compilers, then probably you would like to get into the ecosystem where a lot of programs are run. So growl and Truffle fit that bill in a sense that they're written in Java. They're easy to get started. If you ever wanted to create a compiler, this is maybe a cool place to start. And then just to follow up, there are no people love languages, but mostly people hate languages. And if nobody hates a language, that means nobody is using that. And well, different languages have different trade-offs at their quirks. Doesn't mean that they're bad or good. They mean just they're different. So with all that in mind, this is everything that I wanted to show you. Thank you for coming. This is it. I think we have 7 minutes, so if you have any questions, there is a microphone. I'm not sure. Maybe you can yell and I can repeat.
Yes. My problem is a bit different. I don't want to create a simple language, but I want to create a simple extension of Java. So I want to start from Java and add my syntax on top of it. Do you think that these tools are good for this task or not?
So the question is, I'll just repeat so it's on video. So the question is, if the problem is not to create a new toy language or the new language itself, but the problem is to extend the Java and maybe start with Java and add some syntax on top of that, and if the Truffle and growl, if this framework is good for that. That's a good question. It's interesting. It depends on how much you want to extend language. So maybe if you just need a couple of tiny things, it's easier to just implement them in the OpenJDK. Well, the runtime and the software it's open source, so you can just go and add the Elvis operator into the OpenJDK project and have it there. If you want to create a different language altogether, then you would probably need to small changes would probably be harder with this, because you still need to parse the source yourself if you would like to have a different program than Java, and then you have to translate that into the terms of.
But there is the underlying grammar of Java 8, so and I don't know, and use these tools to create my compiler. That's what I was thinking to do, but not sure if it's possible.
Yeah, there are tools to create that. There is a grammar for interleader for Java, so you can parse that and you get the you get the AST. The problem that you will face is that when you convert that AST that you get, right, which is not it is not like the Java program in the JVM sense. You get the representation of this Java program, and then you will have to convert that to the Truffle implementation of Java. So it might be not complicated to do, but if you start from scratch and yourself, you'd probably be quite cumbersome to do to handle the cases and to implement, because you will have to transform the whole tree. So there might be, so Java runs on Truffle, but they plug the growl as the JVM CI compiler. So they take the representation and then they work on the internal JVM representation of a program to enable those things. So you will have to recreate quite a lot of effort to get there. But it might not be like a rocket science in the sense that it might be very straightforward because you work with Java things and you can transform straightforwardly.
Thanks.
Thank you. We have another question.
Just a remark to that. I think that was one of the showcases of JetBrains' MPS system, to have Java as a language and just extend it, but then you have to use the MPS framework. So it's not trivial, but if you have a considerable change, I guess maybe a way to go.
Great. So the remark is, again, to repeat just for the video and the sound. So the remark is that there was a product called MPS by JetBrains, and it was for creating not the managed language, different languages on top of the Java, and you could add the syntax and the grammars very easily to the language. So if you would like to extend the language, you could try using that. I cannot say how much JetBrains actually is working on the MPS right now and how much they're promoting that. I know that they had these extensions where you could specify the tables of data in your program syntax, and they would convert that somehow to like hash maps or something. And that was a cool feature. So that might fit the bill if you want maybe a little bit more sophisticated extension mechanism just to in terms of defining new grammar and syntax. Maybe not. But this is the possibility that you would like to consider. Do you have any more questions? If not, cool. If you have any more questions, ping me on Twitter. I'd love to chat. Thank you again.